We will discuss the two most important equations of electrostatics, and they are Laplace and Poisson's equations. Okay. So, I know from Gauss law in differential form states that del dot E is equal to rho upon epsilon naught, where rho is the charge density enclosed in a small volume. This is Gauss law. Okay. And if I have a loop, okay, and if I move on this loop, or say if I want to know that what is the change in electric field when I move on this loop, then precisely on a closed loop E dot dl is 0. Okay. Either you move in the counterclockwise direction or you move in the clockwise direction, you would find that always this will be true no matter what the conditions are, that on a closed loop E dot dl is 0. But what if we have an open path? If we have an open path like this, if I have a path which is going from A to B, if I move from A to B, now it does not matter if I am going from A to B or from B to A. Okay. I can say that this, and if I am varying my E on this path, then I can say A to B E dot dl will not be equal to 0. Okay. E dot dl will not be equal to 0, I know this. Okay. And from the definition, basic definition of electrostatics, I can easily say that this E dot dl is the potential difference between these 2 points. E dot dl is the potential difference between the point A and B. So, I can write that integral A to B E dot dl is equal to Vb minus Va. I can say that. Now, from the basic theorem of gradients, I can write this as gradient of V dot dl going from A to B. Gradient of V going from A to B. Now, here V I know is a potential and it is a scalar, and behind this there is a very strong mathematical statement, that is why I can write like this. Although mathematically I can write like this is true, but I also know that del cross E is equal to 0. Del cross E is equal to 0, and I would like to say here that E is a vector field. Any vector field if its curl is 0, any vector field if its curl is 0, then it is equal to a gradient of some scalar field. Remember, this is this is always true. If you take any vector field, it need not be an electric field here, let it be any vector field, if its curl is 0, if you find that the curl of a given vector field is 0, then that vector field can always be represented as gradient of some scalar field. So, it means I can write that E vector field is equal to gradient of some scalar field V, and I call V as scalar potential. Okay. So, this is nothing new, you all know this, you all have done read lot about this, but here what we have done, we have represented E in terms of V. We have represented a vector field in terms of a scalar field. Okay. But how this Gauss law would look when I represent E in terms of V? How this Gauss law would look like? Can you tell me? This Gauss law is the fundamental of electrostatics. everything depends on this Gauss law. So, now it is very important that this expression that I have got for E in terms of V, I should be able to read this Gauss law in terms of V. I should be able to read, that is, I should be able to recast this Gauss law in terms of scalar potential V. When I do that, I get a very interesting equation, and that equation is, if I simply put that there, then what I would get here is del dot minus del V is equal to rho upon epsilon naught. Okay. And I know that this is equal to del square, this is equal to del square. So, I can write from here that this is equal to del square V is equal to minus rho upon epsilon naught. So, this is even more interesting. This equation is a very interesting equation, because what it says, if you know just a scalar field, you know just a scalar potential, you can actually extract all the information in the surrounding region. You can calculate electric field, and if you know the scalar potential, you can calculate the small charge that is enclosed in a small region around that point, say Vx. If I am calculating V, if I know V at point x, then I can calculate the charge also, isn't it? So, it means this equation del square V is equal to minus rho upon epsilon naught is called the Poisson's equation. This is the Poisson's equation, okay? And again, it is an important equation in electrostatics, and just in a moment we would see that why it is so important. So, here what we have is the famous, this equation is called Poisson's equations. So, if there is no charge, if I choose a region, there is no charge in that region. So, what happens to rho? What happens to rho in a region? 0. Okay. So, if there is no charge in a given region, if I choose a point and I draw a small volume around that, and I happen to see that there is no charge near that region, in that region, then del square V is equal to 0. Okay. So, it means if rho is 0 and this rho is 0 in a small volume, okay, this rho is not giving you for the entire space. I am choosing a small volume and I am telling that if rho is 0 in a small volume, then I can say that del square, then the Poisson's equation becomes del square V is equal to 0. And this form of the Poisson's equation, is called the Laplace equation. This is called the Laplace equation, and this is not very specific to electrostatics. You must have seen this equation in heat, you must have seen these equations in mathematics, okay. You must have seen this equation even when you were doing Newtonian mechanics in gravitation. You must have seen this equation, while solving the wave propagation in undamped medium. So, you have seen this equation everywhere. This is a very standard equation called the Laplace equation. But I see a problem in electrostatic with Laplace equation. My rho is 0, V is 0. If I say rho is 0, V is 0. So, there is nothing further, I do not have to investigate anything, isn't it? If suppose I find a region which does not enclose any charge, it means from the Poisson equation the right hand side is 0, del square V is 0. If del square V is 0, it means there is no potential. Only charge will generate a potential. When there is no charge, there is no potential. So, Laplace equation goes to 0. Okay. So, this is not a very good picture, means the electrostatic ends there, story ends, nothing more to say. but actually that is not the case, because when we choose rho 0 we are choosing a small volume, but there might be several charges available, several charged particles available in the space elsewhere, and they will contribute to some potential at the point where we are keeping our rho 0. So, actually V will not be 0 even if rho is equal to 0. Even if rho is 0, V need not be 0. Okay. Why V need not be 0? Because there are other charges, and I mean maybe it looks little abstract now, but we will see, you will see that it is actually not 0. Okay. So, what we do now, we try to see the Laplace equation in Cartesian system. Okay. We will go ahead with Cartesian system, because now you can convert any system into any system using the formula that we have done. So, we will move on with the Cartesian system, so that you are able to understand the concepts well, and then you can convert them into any system you want. So, let us see this Laplace equation. So, what it says, it gives me a contradicting statement at the moment. It says that if I am in a region where there is no charge, then potential should be 0. It looks logical, but not very logical. So, let us consider Laplace equation in one dimension. So, I can write this Laplace equation here. I will expand this. I can write this in Cartesian system as del square V by del x square del 2V by del y square del 2V by del z square is equal to 0. Okay. So, now I say I am interested only along the x coordinate. I am interested only along the x, y, z coordinate. Okay. So, let me take the x coordinate. So, I have del square V by del x square is equal to 0. Okay. So, why I am taking one dimension, I could have taken all the 3 dimensions, but solving it would become little difficult. So, I take in one dimension just to show you that actually if this is 0, V is not 0. If we solve this equation, what I get? I get V is equal to say mx plus c. ये मिलेगा आपको if you solve this equation. बताइए, you integrate this equation twice, you will land up with this equation. So, it means for any point x, even if it is 0, even if x is equal to 0, okay, even if you are at the origin of the space, still the potential is not 0. Potential is equal to this amount c, isn't it? So, it means that always what we perceive apparently may not be true. Okay. So, it is always good to investigate things in detail. So, what we see here, we perceive that because if rho is 0, V should be 0. But when we try to solve this Laplace equation in one dimension, what we see, actually this is not true. This is not true. Okay. So, we get V is equal to mx plus c. So, let me say that at x is equal to 1, V is equal to 5, okay, some values. At x is equal to 1, V is equal to 5, and at say x is equal to 5, V is equal to 0. So, what would be my plot? It should be something like this. Isn't it? So, what is m in this case? What is the value of m? 1? Are you sure? 1? बताइए. Slope is 1. Then okay, 5 by 4 minus 5 by 4. Okay. So, I can say it is almost 1. Okay. So, I can say it is minus 1, but minus sign is important, okay. Do not forget that minus sign. So, I can say that V is equal to say minus x plus what? Minus x plus what is C? It is not a constant, it is an intercept. So, what is C? When I draw this, now C is not an unknown variable, unknown constant, it is an intercept. What is the value? बताइए 5. How do you calculate the intercept? Okay. So, it looks you do not remember what you studied in your class 12. Okay, I take this equation. Okay, you verify this. V is equal to minus x plus 5. Okay. So, actually what this Laplacian equation tells me, what it is telling me? It is giving you an instruction to average V. Okay. Laplacian is an operator, it is a mathematical operator. Like del is an operator, Laplacian is also, del square is called a Laplacian operator. It gives you instruction to average V. If you choose x, a point x, if you want the value of V at some point x, if you want the value of potential field at some point x in space, then this is equal to the value in the neighborhood. You have point x here, you choose a small neighborhood. Let this point be x plus r and this point be x minus r. Okay. So, the average of the value here will give you the value at Vx. So, what is Vx? Vx I can write that is equal to Vx plus r plus Vx minus r. Okay. And these Laplacian, because del square V is 0, so it will not tolerate or it will not have any maxima or minima. Always maximas and minimas would lie at the end points. Okay. Always maximas and minimas would lie at the end point. So, these two important conclusion we get mathematically from by looking at these solution. So, first thing that this del square will always give you, will always try to average V around a small neighborhood. And second, that this Laplacian will ensure that there are no intermediate minimas and maximas. Always minimas and maximas are at the end points. Okay. Is it okay? So, we have seen two equations. So, one was the Poisson's equation, and I can say that Laplacian equation in electrostatic is a special case of Poisson's equation. Okay. So, when rho goes to 0, so general equation is del square V is equal to minus rho upon epsilon naught. So, it is very interesting that in the root of everything lies the Gauss law. From Gauss law we can derive Poisson's equation, from Gauss law we can derive Laplace equation. So, it means Gauss law is the heart of electrostatics. Anything you want you can calculate. Now, let me elaborate little more on Poisson's equation. We have seen the special case of Poisson's equation. So, similarly we can solve these equations for in 2 dimension and 3 dimension too. Okay. And the solution of these equations are called harmonics. Del square V by del x square, del square V by del y square, del square V by del z square. When you try to solve this equation, the solution that you get are called harmonics. Okay. And you all know that. You all know that. आप लोग ने जो है जब भी कोई wave propagating आपने किया होगा, या even if you have done resonance circuits जब आपने solve किए होंगे, so you would have seen that you would have got similar type of equation. Okay. And the solution that you get is called, I mean you change some integer n and what you get is the higher harmonic, that is the higher value or the higher value at which this equation will get satisfied. So, the solution that we are going to get out of this Laplacian equation is the harmonics of this equation. So, now we go to Poisson's equation again. So, my Poisson's equation is del square V is equal to minus rho upon epsilon naught. Okay. So, it means if I know the scalar potential at any point V, if I know the scalar potential at any point V in space, I can give you the electric field, I can give you the charge enclosed, I can give you everything. What I need to know? Only the scalar potential, and I can calculate electric field, I can calculate the charge enclosed in the entire space or in a small volume, I can give you everything. But what if you know rho? What is the problem now? Till now, if I know potential, I can calculate rho and E. And if I calculate rho and E, I have given you all the relevant data about an electrostatic field. That is what all I need in an electrostatic field. But if suppose you know rho, you do not know V, you know rho is given, then how will you calculate V and E? It is the inverse Poisson's equation. Inverted Poisson's equation will give me, if I know rho, then I will be able to calculate V. In other words, if I can solve this equation, then through the solution I can find V for a given rho, isn't it? If I know the solution of this equation, if I can solve this second order differential equation, then from the solution of that second order differential equation for a given rho I can calculate V. हो सकता है जो solution होगा उसमें जो भी रो की वैल्यू है वो आप रख दीजिए, आपको एक पॉइंट पे V मिल जाएगा. Okay, but solving the second order differential equation is not as easy as we think, because it will take maybe 5, 6 or 7 pages to solve this equation. So, what we do, we go back to our old Coulomb's law and we take the help of Coulomb's law. Okay. So, let us go back to Coulomb's law. It states that the Coulomb's law states that a potential at a given point I can say that V is equal to minus 1 upon 4 pi epsilon naught infinity to r dash upon r dash square dr. It is the work done in taking a unit charge from infinity to an electric field. Okay, that is why it is from infinity to r. Okay, this is the basic definition that we read much earlier, and that is why this negative sign also comes in here. Okay. So, when I solve this equation, what I get here is 1 upon 4 pi epsilon naught, there should be a q here, okay. So, I have q by r, okay. But you see here this equation is slightly tricky. What is V? Potential. And what is this? Unit vector. So, I need to have there is a direction coming in there, but I do not want a direction to be associated with V. Okay. So, if I can represent it in a better way where I do not have to use this unit vector, then I will be more comfortable, because it is a scalar field and I have to always associate unit vector here. So, that does not look very good. Okay. So, what I can do instead is I can write that V is equal to 1 upon 4 pi epsilon naught rho upon, just check if I am right, rho upon r integral d tau. Rho is the charge density. The same equation can be recasted like this. You can rewrite this equation like this using your Gauss law of divergence. You can use this, where rho is the density, and if you solve this equation, if you solve this Poisson's equation, you will see that your solution looks like this. Your solution looks like this. Okay. So, now there is no issue at all. If you know rho, I know that this is the solution of this equation. Okay. So, if I know rho, I can calculate V. If I can calculate V, I can calculate E. Okay. So, this is again an old but a golden equation. We all knew this, we have been studying this for long time, but actually this is an important equation because it is actually a solution to this Poisson's equation. Okay, is it clear? Any doubt? Any doubt till now? No doubt? So, here this side it is clear to you. So, now you see that this Poisson's equation actually we can solve them in a system. This was, what is this? This is for an isolated charge. Here Q was isolated, there was one Q, you were moving only one single individual charge from infinity to a given electric field. But generally my system might not have just one single Q, there can be several charges. Okay. So, it is very important if I have to solve such differential equation, if you know you have some initial value and final values for a differential equation, how the system would behave at the start and how the system should behave at the end. So, these conditions, what in mathematics we call initial value and final value, here we call them boundary conditions. Okay. So, whenever we have to solve this equation, I mean here we were lucky, we were having only one charge and we can calculate explicitly V at any given point. But we might not be so lucky when we are solving some practical systems, because it is very much possible that there we have more than one charge and the system boundaries are not very symmetric. They are not, neither they have spherical symmetry, nor they have cylindrical symmetry, nor do they have Cartesian symmetry. So, then what you will do? So, it is very important, even if there is no symmetry, we know the system behavior at the boundaries of the region. It might be any boundary, it can be a very arbitrary type of curvilinear boundary, no matter, but we should know that what are certain values at the boundaries. And these boundary conditions will be, with these appropriate boundary conditions, you will be able to solve this Poisson's equation and you will get a unique solution. Okay. So, as far as this Poisson's equation is concerned, there are two boundary conditions. There are two unique boundary conditions. So, what are boundary conditions? I will write down here. And these boundary conditions give you the system behavior at the edge. Edge means the surface, boundaries, at the edge of the region. It could be the starting edge or the extreme edge, whatever. This is very important. Okay. So, what would happen? I would know if at the edge, when I am at x is equal to infinity, if my V is 0 or infinity. So, this will help me in terminating the solution in getting a precise solution. Is it okay? So, So, before going into the boundary condition, it is I will not be able to complete boundary conditions today. So, I would want to take it in the next lecture, but before going to boundary condition, I would like to again tell you what we did here today, because now we will start with electromagnetism, and the whole of electromagnetism is based on boundary conditions, and all boundary conditions are based on this equation. Okay. So, you have to understand that from where this equation comes. This equation comes from the Gauss law. Gauss law says that if I have, Gauss law is always associated with closed surfaces. Ampere law is associated with open surface. Okay. I say that B dot dl is equal to mu 0 I over an open surface. I say that del dot E is equal to rho upon epsilon naught over a closed surface, where rho is a charge enclosed in a small volume. Okay. So, now if I know that E is an vector field, then and its curl is always 0. In an electrostatic field, curl of E is always 0. So, if curl of E, curl of any vector field, if it is 0, if curl of any vector field is 0, then it can always be represented as gradient of some scalar field, and that scalar field I call the potential. I call that scalar field as potential. Okay. Now, this potential I should be able to represent, or I should be able to represent the Gauss law in terms of V, and when I do that, I get the Poisson's equation. When I try to represent the Gauss law in terms of V, then I get Poisson's equation. And with Poisson's equation, with the help of this equation, if I know the potential at any point, I can get field and I can get the charge. Okay. And when the charge enclosed in any medium, charge enclosed in any medium is 0, then the same Poisson equation becomes a Laplace equation. And if del square V is 0, it does not mean that V is 0. We have seen that V can have some finite values, although in that small region Q is 0, but there are several other charges in the region, in the whole space, and those charges will contribute to some finite V, some finite potential at the point where we want to calculate V. So, we always see that del square V is equal to 0 will lead to some finite potential, okay, even at the origin. So, it means that rho 0 does not mean V 0, it means there can be electric field, there can be potential, but I can always find a small region where rho is 0. Okay. And then the last problem was that if I know rho, how to calculate V. So, it is called inverted Poisson's equation solution, inverted solution to Poisson's equation, and that solution is equal to this expression, and this expression we got, you will get, we will solve this expression, we will solve this Poisson's equation, but for solving this Poisson's equation we need to know the boundary condition, and this solution we got only by using those boundary conditions. There are two boundary conditions here, and we will discuss both of them in detail in the next lecture. So, if you have any doubt till now in this lecture, you may please clarify. Okay. And I would also suggest that a bit you must go through your electrostatics, basics of electrostatics, because now on we would assume that you know most of the electrostatics that you have done in your earlier classes, and we would move on. Now, we will move on to electromagnetism. Okay.